There we go. So it's a great pleasure to have Jim Halverson here today to tell us about neural networks and quantum field theory. So go ahead, Jim.
All right, can everyone see my screen okay? Is the aspect ratio all right, or is it a little weird?
Works for me.
Looks good.
Okay, I've had some aspect ratio problems because I'm, anyways. Yeah, thank you. Thanks for the invitation. It's great to be telling you about my work on neural networks and quantum field theory with my students. First time speaking, I think, to the UBC group, which is a lot of fun. It's always good to get to know different groups that are out there, particularly ones as excellent as yours. Yeah, so you know, neural networks are a bridge. I like that. So right, so like I said, this is based on some work with my students who you'll see pictures of in a second. And really, this is about trying to connect techniques from physics and techniques from deep learning. I have been doing sort of string math related things and string compactification related things for years. So I'm very used to the idea that our techniques from high energy theory are applicable to math, but normally it's to algebraic geometry and topology for me. And neural networks are really more about statistics. This is about applications of QFT to neural nets from a statistical perspective. Generally, there's a lot of work trying to connect physics and machine learning these days. So two quick shout outs are for the Institute for Artificial Intelligence and Fundamental Interactions, which is a new NSF AI Research Institute that we are very proud to be a part of. It's joint between MIT, Northeastern, Harvard, and Tufts. And we're sort of interested in both arrows in this direction. Can AI drive physics and math progress, and can physics and math drive AI progress? Simultaneously, we've been doing a physics and machine learning seminar series online. That's a follow-up to the meeting that we had at Microsoft Research last year that I saw Jamie at. And we've been going online with that, and it's been a lot of fun. So if you're interested in that, sign up here. And those are some of the ways that you can connect at the physics and machine learning interface, but things are growing a lot. So these are my students, Anandita and Keegan. I am very glad that this says 2022 and not 2021, because it means I get to keep them for a while before they go off into the wild and change the world. They're fantastic. They are working extremely well together, and I'm having a lot of fun with them. So Anandita wants to be in high energy theory, and Keegan wants to be in machine learning, and they're not applying until at least next fall. So keep an eye out for them when they do apply, but it'll be a little while. So I'm going to try to convince you that neural networks are in some sense equal to quantum field theory in this talk. There are often sort of analogies that maybe people would put in quotes, connecting ideas in physics to ideas in deep learning. I would say with a dose of humility that this is a much more direct correspondence. This is not some hand-wavy thing. I'm going to be rather explicit, and I'm going to be using techniques from quantum field theory like Feynman diagrams to compute correlation functions of neural network outputs, for instance. Generally, what we want to do is import the essence of modern quantum field theory into neural networks, and I don't have to tell this audience that that means Wilsonian EFT and renormalization. But before I get there, I need to tell you a little bit about what's been happening in deep learning. I think everyone in STEM fields now knows that what has been happening in computer science the last 10 years, when you count the start date, depends a little bit on the person. But what's been happening really is a revolution of sorts, and they're getting really fantastic results. It is a time in their field that they are going to remember for a very long time, and it's exciting. So it goes under the name deep learning, and I'm going to tell you about 3 different types of deep learning. There's supervised learning, which learns to predict outputs given inputs. So given an image of this 3 or that 3 or that 3, you would like some algorithm that can learn how to predict 3 regardless of which version of 3 it is. So you're learning to predict outputs given inputs. Then you test on unseen data so that you're not just testing on the things that you trained on. There's many simpler algorithms for doing this, but recently deep neural nets have taken over. This is a super famous data set on the right called MNIST, and they have a couple thousand images of this type, and this is what you train on. So when you hear about deep learning in physics, this is the usual thing that people mean is predicting outputs given inputs. It's just a function that predicts outputs given inputs. But there's different sorts of ways to use functions, not just predict outputs given inputs like that. You could think of a function as sort of being a decision module and some little AI agent that's exploring some state space. It's exploring the state space according to a policy, which is a map from states to actions. And if you were to draw actions given the state uniformly from some uniform distribution on some action space, we would call that a random walker. But ideally, if there's some notion or goodness or badness in the system, you should be able to use behavioral reinforcement to update the policy function so that the agent acts better and better over time. And so that's the idea behind this type of machine learning called reinforcement learning. This is the thing that is behind all of the progress in Go and in chess. If you haven't watched AlphaGo on Netflix, it's a wonderful movie. And even though, despite being wonderful, it's actually out of date. They have a better algorithm now called AlphaZero that is not only the world champion in Go, it's also the world champion in chess. And there's all sorts of interesting things to say chess-wise about this plot. One thing is that some of the human, people ask about interpretability of AI. In chess, it's actually a pretty easy thing to do because all you need to do is you study 10 of the 6 rollouts of games played by the AI, and you see how regularly it plays certain openings versus others. So this is a plot that demonstrates how various openings that humans came up with were learned by the AI on its own, and how frequently it played it as a function of time. So this is a famous defense that was played for quite a bit between hours 2 and 6, but then it doesn't play it too often anymore. We had a paper last year on using similar techniques in string theory. In string compactifications, as you know, there are many consistency conditions that have to be satisfied. So if you view each of them as some reward that you can get, and you have these tiered reward structures for tadpole cancellation, that's the Gauss law in the extra dimensions, K-theory, and supersymmetry, and you have these 3 tiers, you might hope to have an AI that can come up with consistent string compactifications for you. And we found that this is possible using something called an asynchronous advantage actor critic. And one of the interesting things about it is for a while it plateaus. So this is a little reminiscent of punctuated equilibrium in evolution, that sometimes when a system is evolving, or in this case, a reinforcement learning agent is updating, it gets stuck in a certain performance threshold for a while until there's some stimulus in the system that is so drastic that it causes it to get better quickly and then find another plateau. So that's what's happening here. Most recently, I should have updated this. This actually did appear a week or 2 ago. This is our new paper, Learning to Unknot. The unknot problem is a famous fundamental problem in knot theory. It's connected to various other famous conjectures in low-dimensional topology. And fundamentally, the essence of the problem is, given a complicated representation of a knot or an unknot, you want to know, can I find the sequence of moves that, if it is an unknot, trivializes it into a circle? So this figure here, this actually is an unknot. There is a sequence of moves that can trivialize this thing to a circle without ripping or tearing. And that was sort of the essence of what our paper was after. We use reinforcement learning to do that, not just to decide, but actually to find the sequence of moves that trivializes the knot. And finally, a third type is what we call generative models. Generative models are a different type of deep learning. The basic idea is to generate or fake or simulate data. Concretely, what that means is that the neural network is some powerful function that takes some draw from some noise distribution and then maps it into some target data distribution so that it's an effective draw from some target data distribution. Before training, it just takes noise and spits out noise. But after some amount of time, it takes in noise and it spits out images like this. When you look at these images, these are remarkably high def and very convincing, given that these people don't actually exist. So these are generated by a neural network given noise, something often as simple as draws from a multivariate Gaussian to arrive at something that is realistic looking images of people that don't exist. In physics, you might want to do this. Well, it's called JANT4 for electromagnetic calorimeter, or 30 million or something like that. That type of generative model called a GAN is way, way better for simulating the simulator. We did this in string theory earlier in the year. You might ask concrete questions like, if we were to take a random matrix approach to simulating the string landscape, how is it that we might take actual string data and learn to draw random matrices that are more reminiscent of the ones that actually arise at string compactification? So those were some of the things that we were after. But my point isn't any one of these projects. It's that there are these very different ideas of how to use neural networks in deep learning. Predict outputs given inputs, have an agent that learns how to behave intelligently where the neural network is learning how to pick actions. Or alternatively, a neural network that's just learning how to simulate something that you care about, in this case, pictures of humans. Okay. So those are very different ideas, and neural networks are the backbone for all of it. So from a computer science point of view, one of the big questions is, if neural networks are the backbone of deep learning, how should we understand them? And today I'm going to take full stop, no apologies, a function space perspective on neural networks, not a parameter space perspective. And this is particularly natural because in quantum field theory, in the path integral, it's a function space perspective on quantum field theory. In particular, we have a distribution on the space of quantum fields. This is how the path integral works. And so the idea is to model neural network distributions by Wilsonian effective field theory. The non-Gaussian coefficients can be understood by GP limit symmetries in correspondence with technical naturalness. And in particular, under our G-flow, you might imagine that some of the parameters are going to become irrelevant and move you towards a notion of minimal distribution. So this is what we're after, and I'll make some comments about CS at the end. For physicists, this is actually a natural thing if you've ever trained a neural network yourself, because you know that if you restart your code, you're going to get slightly different results. Why is it? It's because when you start your code, unless you set the seed and it's reproducing exactly the same neural network, it's doing a different initial draw of the neural network, training it, and then you therefore end up with a different trained neural network because you started with something different. Put concretely, the neural networks have some concrete architecture, but that's inducing draws from some function space distribution, and that's really the way to think about the initial neural nets. So if you rinse and repeat, you'll get different results. Right. Concretely, the place that I'm going is that many of these neural network architectures at initialization and also under training are drawn from close to Gaussian distributions. And the second that I say close to Gaussian distributions, you say, okay, what about the non-Gaussian terms? Can I do perturbation theory in them? And of course you can. This is the backbone of perturbative quantum field theory, and it's surprisingly a useful way to think about neural networks. So this idea that perturbative QFT is all about near Gaussian distributions and computing correlation functions, we're just going to import this directly into neural nets. Okay, so that's my introduction, the motivation at least. I'm going to tell you what neural nets are, tell you about asymptotic neural networks. Crucially, in the asymptotic limit, they're going to be drawn from a Gaussian process, which means from a Gaussian distribution on function space. Then I'm going to take finite n. N is going to be my parameter that I take to infinity to define the asymptotic neural network. So the finite n ones are going to be drawn from close to Gaussian processes or non-Gaussian processes. And that's when you should be doing effective field theory. And we'll wrap it up with Wilsonian renormalization in these neural net non-Gaussian processes. So I'm going to launch in a second into what neural nets are, but are there any questions on motivation or anything I said? No? Okay. Okay. So here's my introduction to neural networks. I have my watch, so I'm going to try to keep an eye on the time. For the purposes of this talk, if you haven't heard of neural networks before, you should just think of them as these are powerful functions. There's various universal approximation theorems that can quantify what powerful means. Really what it means is that they're extremely good function approximators in a way that analysts will make precise and whatnot. But for this talk, powerful function. So a neural network is just a function, really a family of functions parameterized by some continuous learnable parameters theta. And there's also a discrete hyperparameter n that I'm going to bake into my definition of neural network here because we're going to take an n to infinity. There's some input dimension, there's some output dimension. You can play with whether these are real or complex and whatnot, but will be real in this talk. And the basic idea is that given some initial neural network with some concrete values of theta, what happens when training occurs, either to predict those handwritten digits or learn how to play chess or generate images of people, is that these thetas are updated such that you improve performance in some concrete measure of what performance means. And over time, what GPUs are really good at is quickly training these networks so that you end up with good performance. Concretely, part of the reason that they're powerful is that neural networks often involve many parameters and composing many subfunctions. So just like as you might think of a brain as having one function here that passes information to another neuron and to another neuron and so on, and in the process, you're combining many little mini actions together. That's a reasonable way to think about how neural networks are made. So the most famous type of neural network of these really powerful functions, most famous because it was one of the earliest, is what's called a fully connected network, also known as a feed-forward network or a multi-layer perceptron. I'm going to give you a super concrete instantiation of this in a little while. So for here, what I want to talk about is this image. So the basic idea, the essence of this type of architecture is that it takes some vector at input, and it's going to pass the information related to that vector through the network and do some computation in it. And what it's going to do is it's going to compose a bunch of two-step things. The first step is a parameterized affine transformation, and then an element-wise nonlinearity acting on the vector that comes out of the affine transformation. So network comes in, vector comes in, affine transformation, nonlinearity, affine transformation, nonlinearity, and so on until you're at some desired output. So the combination of affine transformation and nonlinearity is called a layer. The number of layers is represented by this direction in the picture. This is called the depth of the network, hence deep learning or deep neural network. And this direction represents what's called the width of the network. Okay? So these affine transformations that are acting on the vectors at the different stages of the computation, of course, they're giving you some vector out, and the dimension of that vector that comes out of the affine transformation is what is the width. So these functions have parameters that are drawn from some distribution, and these parameters are represented by these lines in between the nodes. But really concretely, this network just is some function where these b's and w's are parameters of vectors, parameter vectors, and parameter matrices. So you may have seen this before, but if this is a little fast, you'll see a super concrete one-layer version in just a little while where it'll be totally obvious what I'm doing. There's other architectures too. The way that which little tiny functions you take and how you compose them together, that defines what's called an architecture in the literature. And depending on how you choose those functions and how you combine them together, you get different architectures like convolutional neural networks or autoencoders and whatnot. So these are common architectures out there, and you can get better performance by using different architectures for certain purposes. That's sort of the 101 of deep learning. So just going back to the examples I gave you, we have these super powerful functions. So what are they doing in these different types of deep learning? Well, in supervised learning, it's just a powerful function that's learning to predict the outputs given the inputs. But in generative models, the neural network is the powerful function that maps, draws from some noise distribution to draws from some data distribution. And in reinforcement learning, the neural net is a powerful function that, for instance, learns how to pick intelligent state-dependent actions. So instead of a random walker that draws from a uniform distribution regardless of the state, the neural network, via training, will learn how to localize for certain states the density of the action-space distribution onto certain actions, because given certain states, certain actions are more likely to be good. Okay. That's the end of this section. This is really the beginning of my talk coming up here. This is sort of the new stuff and the stuff that we contributed. But the background on deep learning and why we care, the TLDR is just that neural networks are the essence of deep learning as has been applied for the last 10 years. So we want to understand them. Questions? I will take a serious pause here to have a sip of water, and if you guys have questions, I'll take them. Okay. Well, in that case, I will continue. I wish I could see everyone all at once while I give these talks, but I'm still a Zoom amateur. All right, so okay, so those are neural networks, and we want to understand them. And the way that I have set it up conveniently, these architectures have some parameter n that I'm going to take to infinity. That's going to define an asymptotic neural network. And the punchline is that we're going to want to consider asymptotic neural networks that are drawn from Gaussian processes. And I'll explain what that means, and then I'll tell you why it's effectively free field theory. If I tell you that that is effectively free field theory, then I should have some dictionary that I can set up. The inputs of the neural network in that case are the external space or space-time points. What is called the kernel of the Gaussian process is the analog of the Feynman propagator. The asymptotic neural network itself, the function f of x, is the analog of the free field. And the log likelihood or the log probability is what we would call the action in physics, the free action. And crucially, the free actions in, the actions in free field theory are Gaussian, hence the connection to Gaussian processes.
Sorry, this is probably obvious, but can I just ask, your nonlinear function sigma, is there a nice way to think of a dictionary entry for that?
That really determines the function f itself.
Okay.
But normally the way that we think about deep neural networks is with a bunch of parameters and a bunch of nonlinearities, and we think about how we build the function itself, which is sort of a parameter space and architecture view of the neural network. But what this perspective is advocating is that we should think about it from a function space perspective. So indeed, the choice of nonlinearity affects the function f itself, but really we're going to think about a probability distribution on the space of functions.
Right. Okay. So should I think of there being different classes of free fields corresponding to different choices of f's, or should I think of it as in this dictionary you've like modded out by the choice of different nonlinearities?
I can run this game I'm going to play today for many architectures, but every architecture in principle corresponds to a different field on the other side. Where every architecture, if you were to draw a neural network in that architecture, is some function, and we want to ask what is the function space distribution from which that function is drawn.
Okay, and there's enough, because usually I think of free fields as being simple, but you're saying there's like enough different types of free fields to match these types of.
That's right. That's exactly right.
Thank you.
In particular, the analog of the free field, the action, the inverse of this operator k is going to be something that appears in SGP, and each asymptotic neural network is going to have an associated kernel, and that's the thing that specifies the correspondence.
Okay, thank you.
Yeah, great question. Anyone else? All right. So there's only one in this whole business, and even like when you hear deep learning talks about this sort of stuff, there's only one trick, and the trick is the central limit theorem, and I need something to go to infinity to be able to apply the central limit theorem. So let's talk about where that is. So I'm going to define an asymptotic neural network. So when your neural network has some discrete hyperparameter n, I'm going to be agnostic right now as to what it is, and then I'll give you concrete examples. But suppose that it has some discrete hyperparameter n that enters into its architecture. And I want to take the n to infinity limit, but I don't want to do it for any arbitrary n. I want an extra property to be true. The crucial property that I want to be true is that as I take the n to infinity limit, what I'm doing is adding an infinite number of parameters, which themselves are IID random variables, identically and independently distributed. Okay. And I'll get to why that is in a second. But the most concrete case is that when I consider the networks of this type that I had, if n is the width of the network, this will be something that is relevant. If it's the depth, it's not something that's relevant. The crucial thing that I want is I want to take a limit that in that limit, I'm adding an infinite number of IID parameters. Okay. So there's all these parameters in the neural network. And as I take the width to infinity, these matrices are deep in the network. They're n by n matrices where n is tending to infinity. And each entry in the matrix is some parameter. So this computation involves adding up a lot of random variables. The reason that that's relevant is because if you add n independently and identically distributed random variables, that's IID, then you take n to infinity, the sum is drawn from a Gaussian distribution. Okay. You can slice the neural network at different points to use this fact at various different points, and I'm just going to focus on the output. So the affine transformation that takes me to the output vector is going to be an n by d out matrix. There's an n vector also, but there's an n by d out matrix. And that n by d out matrix, as I take the infinite limit, as that acts on the post activation here to give me the output, what it's doing is it's taking a sum of an infinite number of random variables, the parameter itself. And so this thing is, what that means is that the output itself is drawn from a Gaussian for fixed input. And as a whole, what it means, because it works for any fixed input, and you can vary the input then, it means that the function as a whole is drawn from a Gaussian distribution on function space. And this is known as a Gaussian process in the literature. A Gaussian process. So that's the key thing, that I'd be able to take an n to infinity limit where I'm adding an infinite number of IID random variables, and then I apply the central limit theorem that tells me that my output is drawn from a Gaussian. Most architectures admit a GP limit. Gaussian processes are rather, I don't know when exactly, but a decades old at least subject in Bayesian inference. And connections to neural networks between neural networks and Gaussian processes started in the 1990s. But then the field was quiet for about 20 years, and there's been a flurry of interest since then. And that's what this is about. Crucially, most architectures admit a GP limit, okay? So the essence of why architectures admit a limit in which neural networks are drawn from some Gaussian distribution on function space is because of the central limit theorem. So if you get clever and you find some clever way to take an n to infinity limit where you're adding n independently and identically distributed random variables, you're going to get a GP. And here's a lot of evidence that GPs are rather general. So what does this mean? In this limit where I have an asymptotic neural network that's drawn from a GP, it just means that I can write the probability distribution in this way. Notice it's quadratic in F, it's Gaussian in F, and there's some operator C that is tying together the Fs. The functional inverse of C is defined by this equation, and K is called the kernel. If you think of the distribution as e to the minus s, s is the log likelihood, which is this function. And of course, one thing that we know in physics is how to compute correlation functions. It's just the expectation value of the product of f's evaluated on certain inputs in this particular distribution, right? Something that I maybe should say now that I can elaborate on at the end is that in some sense, the central object in machine learning is the function space distribution at initialization, and then how under training the function space distribution moves to some trained distribution. Okay? The learning process is a trajectory through function space of some initial neural network to some target neural network that is well trained. But if you did that 10 to the 500 times, you would have 10 to the 500 draws from some initial density, and the density would move somewhere else. So if you can control the function space distribution of neural networks at initialization and under training, you have solved an essential aspect of the learning problem. Okay. So we're going to do exactly what we do in physics. We don't ever actually measure the distribution of the standard model directly, right? What we do is we compute scattering amplitudes and correlation functions, the higher moments of this distribution from a statistical perspective. And then given experiments, we infer information about what the parameters are based on the experiments and how they're correlating with the correlation functions, okay? So we can define endpoint correlation functions. Free field theory is exactly like a Gaussian process. Here's an example. If you'd like, you can think of this as a delta function that is, there's a delta function that is collapsing two input variables to one. But this is quadratic in the fields. This is the free scalar field theory, of course. And so free field theory is a Gaussian process. So if neural networks are Gaussian processes and free field theory is a Gaussian process, you might try to do the normal things that we do in free field theory for Gaussian processes. So the kernel is the 2-point function of the GP, and so in particular, that's the Feynman propagator. So here's an example we're going to do. This is going to be the example I'm going to beat to death throughout the talk. So now in this particular case, my f theta n takes some d in vector, acts with an affine transformation parameterized by W0 and B0 of a matrix and a vector that I add. This maps me into Rn. N is the width of the network. I apply some element-wise nonlinearity sigma. That again leaves me with an n vector. And then W1 and B1 are n by d out matrix, an n by d out matrix and a d out vector. That gives me something in R to the d out. And the full function is this. X comes in, gets acted on by the matrix, shifts by the vector of the affine transformation, nonlinearity acts with the vector, shift by the bias. Okay. These parameters, B0, W0, B1, W1 are drawn from appropriate normal distributions. And, and the asymptotic limit is just the n goes to infinity limit. So because quite literally in this matrix W1, it's n by d out, as n goes to infinity, I'm adding an infinite number of parameters. So the central limit theorem applies, and the neural network's drawn from a Gaussian. This basic idea, this is the result of Neal from the 90s. And Williams gave really concrete ways to compute. Okay. So let's talk about GP predictions for correlation functions. So if there's this correspondence, you might say, okay, let's write down some Feynman diagrams for my neural network correlation functions. So if an asymptotic neural network is drawn from a GP and GP is equal to free QFT, you should be able to use Feynman diagrams to compute correlation functions. Okay, here's our correlation function. At the right, we have analytic expressions for endpoint correlation functions of asymptotic neural network outputs. In particular, the 2-point function is k of x1, x2, which we will represent by this line, connecting x1 and x2. And the 4-point function is kx1, k12, k34, plus all the other combinations, represented by these diagrams. And the physics analogy is that this Gaussian process just corresponds to the non-interacting theory. And in particular, the kernels entirely determine the higher point statistics, just like how in the free theory, the propagators determine all of the correlation functions. So this is I put this in for ML people that may or may not be in the audience. This GP, the infinite width limit network, is the analog of a theory where particles just fly past each other and they don't interact with one another. And that's represented by these diagrams. So to specify, I want to do some experiments. This architecture is specified by the choice of sigma and n, and these certain variance parameters for how we draw the parameters. So sigma will take to be an error function or a particular sigma that we invented ourselves to get translation invariance. And then we have another case where we have the rectified linear unit, which is a particular function that's very famous in deep learning. Given each of those, you can compute this function k. K is the crucial thing for computing the correlation functions, and they have known expressions in these cases. Here are the k's. You might ask, okay, if I have this idea and I want to do Feynman diagram calculations for infinite width neural networks, what I should be able to do is say at some finite n, I want to measure the deviation in the experimental endpoint function from the GP prediction. And then as I take n to infinity, I should be able to see that decay off to 0, right? So for instance, if I want to compute the experimental 4-point function, I just take some number of networks that's like 1,000,000. I sum up over all of them. And on some fixed inputs, x1 through x4, what I do is I compute f times f times f times f, f of x1 times f of x2 times f of x3 times f of x4 for the particular f associated with that neural network, and then compute the ensemble average. That's experimentally how I compute correlation functions of neural network outputs. You can do it for 6-point functions or really any function. But I want to compute delta G4. I want to compute the deviation between the experimental piece and the Gaussian process prediction. This is the thing that you should get in the limit. This is just an analytic function of these k's that I wrote down on the previous slide. So this is just something you hard code in. It's analytic. This is where you do the neural network experiments, and this is the quantity that I want to study. So yes, you can measure the Falloff to GP predictions. So in these directions, I have fixed network architecture, and these are 2-point, 4-point, and 6-point functions. Okay, m is the deviation in the endpoint function normalized by the experiment by the GP prediction for the endpoint function, and there's a notion of background here. But above the background, when you can trust that it's not statistical noise, you can see that the 4-point and the 6-point functions are dying off. And in particular, when you compute the slope on a log-log plot, you realize that the correlation functions are dying off like 1 over n. So there's some concrete experiments that we did, 10 to the 6 neural networks each, computed ensemble averages to get the correlation functions, and then see how it dies off. So the 2-point and the 6-point function die off, but you'll notice in the 4-point and the 6-point function die off, but the 2-point functions actually look pretty constant. There's no dying off going into any of these. What we're doing is a lot like quantum field theory, but part of the fun is realizing where places in our QFT bias for how we do normal QFT don't exactly apply. One of the things that we realized partway through our project is the way that people compute these kernels, these Gaussian process kernels, it doesn't depend on n at all. These functions k are the right 2-point function for neural network outputs for all values of n. What that means is that this is the exact 2-point function. You can show that analytically. And so in your experiments, in fact, you shouldn't see any fall off to 0, precisely because these are these exact 2-point functions. And the fact that we're seeing some noise, but some noise on top of flat lines is what characterizes that we have the exact 2-point function. Okay, just a comment. So this is a little bit different from normal QFT, but one can still compute. So our equation so far, and I'm looking at the timing, is that many asymptotic neural networks are drawn from Gaussian processes. But if an asymptotic neural network is equal to a GP, or at least drawn from a GP, and GP is equal to free QFT, it begs the question, what about at finite n? The asymptotic limit is special. In general, networks are at finite n. And the neural network distribution must receive 1 over n corrections that are non-Gaussian. But of course, this exactly is the essence of perturbative quantum field theory. It's what we would say corresponds to turning on interactions in the physics. And so this is why we think n is equal to QFT. So any time I have an architecture with an asymptotic limit when it's drawn from a GP, when n goes to infinity, then at for some sufficiently large n, I should have a perturbative QFT description of what's going on. Okay. Not a whole lot is going to change. The inputs are still the external spacer spacetime points. The kernel is still the free or exact propagator, where which one it is depends on the example a little bit. The network output is the interacting field, and the log probability is the effective action. So we're going to take our GP action and we're going to encode some corrections in terms of higher order operators. Such non-Gaussian terms are interactions in the field theory, of course. We're going to do Wilsonian EFT, so determine the symmetries or desired symmetries respected by the system of interest, fix an upper bound K on the operator dimension appearing in the effective action, and define delta S to contain all operators that respect the symmetries. Okay. So in our case, right, we're actually doing some experiments. We have, it is, because the 2-point function is exact, I don't need to encode any quadratic corrections. Yeah. On the other hand, the odd point functions can be shown to identically vanish. So that suggests that the odd couplings vanish, which means that the first non-trivial terms you have in the non-Gaussian process part of the effective action are a quartic and a sextic. And in fact, you can show that kappa is more irrelevant than lambda in the Wilsonian sense. So even kappa can be ignored, which is nice because in these concrete examples I'm going to have, it means that this 4-point coupling is a crucial coupling that allows us to get some real headway. So what we're going to do, correlation functions of neural network outputs are defined by an associated non-Gaussian process distribution. And just like usual in physics, we can compute correlation functions in terms of Feynman diagrams. But now I have interaction vertices, right? For every non-Gaussian term, I'm going to have a certain type of interaction vertex. And in computing the correlation functions of neural network outputs at finite n, because at finite n I have these non-Gaussian terms, I need interacting theory fundamentals. Okay. So one of the reasons we wrote a very long paper is so hopefully when machine learning people read this, they don't need to go consult QFT textbooks. There's obviously a lot of technology that we learn in graduate school that help us do these computations. But to people that are uninitiated, standard 5 or 10-page machine learning paper is probably not going to suffice. So we have a very long appendix, and we try to do all of the essence of the terms of QFT there. Okay, so in this non-Gaussian process, we can compute the 2-point, the 4-point, and the 6-point functions. These are actual theoretical equations that enter into our neural net codes. Generally, we set kappa to 0 because you can almost always show that it's negligible. So for instance, the 4-point function has the 3 diagrams of particles flying past each other that are the contribution from the free theory. But then there's this minus 24 lambda. Now you might say to yourself, okay, fine, but why in this theory should I expect my couplings to be constants, for instance? That's an interesting question. So for now, notice that the coupling is left inside the integral because I don't want to make an assumption that it is a constant. So we left the couplings inside the integral because we don't want to make an assumption yet. But of course, in physics, the fact that couplings are constants is deeply related to translation invariance. But if you don't have a translation invariant neural network distribution, you might not be able to have this assumption be true, right? So, so it's true, of course, that the standard model is translation invariant. This is why we have coupling constants, but we're not guaranteed that in these cases. So what we developed was ways, okay, so in the case that lambda is a constant, it's actually very easy to write down an equation that extracts lambda from the 4-point function. This is the equation. Okay. This is the experimental 4-point function. Here's the GP contribution. Then you're dividing by the integrand associated with the tree level correction to the 4-point function, and then you extract lambda. There's a way, if lambda is not constant, to also approximately extract lambda. But regardless, the point is that whether it's exact or approximate, we have a way to extract lambda in these setups. So if effective field theory is effective, we should be able to measure constants and verify predictions. So what are we going to do? Given a candidate effective action for the non-Gaussian process, we want to fix the coefficients of operators in delta S, right? And then once we use experiments to figure out what those couplings are, we want to take those measured couplings and make predictions for other experiments that we can then go verify. This is what we do in effective field theory. There's a finite number of things we measure that make an infinite number of predictions. And that's why it's powerful, because you do a finite number of experiments and you get out tons and tons of information. So in particular, like I said here, our way of measuring lambda is from the 4-point function. So because we use the 4-point function to determine what lambda is, we then want to take that measured value of lambda and plug it into its contribution in the 6-point function and see if it agrees with the experiment. So what we have here on the right is, this is experimental verification. We took the measured lambdas from the 4-point function, plugged them into the predictions for the 6-point function, and computed the perturbative corrections to the 6-point function. We've normalized with respect to the experimental values. So these are our 3 different types of experiments, right? And for each one, it's normalized such that 1 is the correct answer. If you have a perfect theory prediction for experiment, 1 is the right answer. The blue line is what you would get from just the Gaussian process if you don't take into account this correction. And the orange line is computing the leading perturbative correction from the lambda that we measured from the 4-point function. That is, effective field theory is effective, right? So we do some experiments to measure couplings. We make predictions for other experiments using those couplings, and then we go and verify it. So this is just standard EFT. I don't have to tell this to you all, but that's what we do, and it works. Okay. Here's the slide on technical naturalness that I never have time for. If you're particularly if you're a phenomenologist interested in technical naturalness, I can tell you about this at the end. But so far, I'll pause for a second for questions, but I haven't talked about renormalization at all, and that is important. So any questions on the basic setup?
I have one question.
Yeah.
You were saying the higher point correlator is more irrelevant. Normally we think of sort of relevance tied to things having dimensions, so higher point things are suppressed by the cutoff. But
yeah,
nothing carries dimensions here because everything's kind of dimensional. Or maybe they're not dimensionless.
You should do it just like you do. So it's not in these slides, but it's in our paper rather thoroughly. So on one hand, you can do a concrete beta function analysis of any given setup. But you can also make naive scaling arguments often and use those scaling arguments to make arguments for how various parameters should scale. Now, the key thing here is that you have input dimension. There's no dimensions of space or dimensions of momentum. There's input dimension. So in principle, if your neural network had some implicit dimension coming in at input, that's the way that you should parameterize your distributions. So we have a notion of input dimension, and then we parameterize all of our operators in terms of that. Just like you would normally in QFT, that when you, if phi is phi of x, x has dimensions of length, and you organize all of your calculations in terms of dimensions of length, or alternatively dimensions of mass. So you do the same thing for dimensions of input. It's kind of strange to think of inputs to neural nets that way, but depending on what you're inputting, it could have implicit dimensions associated with it.
Did you do your experiments with architectures where the GP structure persists under training, or with architectures that you just kind of initialized?
Yeah, so all of my experiments in this talk are for randomly initialized neural networks, right? So there's some results. For instance, in particular, this paper out of the Google group, that under appropriate types of SGD, I really need to memorize what exactly their one sentence result is. But under appropriate types of SGD, I think for MSE loss, you can show that the GP property persists, right? So this is actually really significant, because if all of the story I'm telling you was only for randomly initialized neural networks and it broke under training, it loses a lot of its power. What I'm claiming is, first of all, that it's very true in the literature that lots of architectures admit this property to begin with. And then crucially, the question is how much it's really true, but there's at least one paper on how this persists under training. So all you need to do sort of this NN-QFT correspondence is to have a GP limit, and then to back off of it slightly, which corresponds to turning on interactions, right? So if at random initialization, if I'm going from the randomly initialized case through some time slicing through training, all I need to be is close to GP the whole way to have an EFT description along the training trajectory. We haven't done that yet, but it's clear that that's the logic, and one hopes that under appropriate types of training it persists. But this is the paper to look at, Lee et al. Yeah. Jamie, did that answer your question well enough too?
I think so. I can think about it a little more.
Sure. Okay. Great.
I have a question about kernels.
About what? About kernels, yes.
Kernels, yeah, you showed us, oh yeah, these pre-examples. How do you get a kernel for an arbitrary architecture?
Right. So in general, it's hard. Yeah. So it depends on the setups a lot. What the kernel is of the GP, it's just the 2-point function. So for instance, the way that we computed them here, we computed them in a couple of ways in our appendix, but the way that we computed them were according to techniques of Yang and techniques of Williams. And for these single layer networks, basically what you can do is just integrate f of x1, f of x2 for the concrete architectures against the parameter space distributions from which the parameters are drawn, right? So you can literally compute the expectation value of f of x1, f of x2 in the appropriate distribution. In general, there aren't any hard and fast rules. It's really a statistical question. But I should say that this other set of techniques of Yang, it's not cited here, sorry. There's another way to compute it under a slightly different assumption that you have a GP coming in. If you have a GP coming in to some activation, then there's another technique for computing it. But in general, there's no hard and fast rules. So step one is always to compute the kernel.
Thank you. Is it something that might be learned in training?
Yeah, I mean, in principle, one could try to do that. One could say, I know that I know that I have a Gaussian process because I can apply the central limit theorem. Can I learn the kernel via some optimization technique? One could absolutely try that via some function thing. But the cases that I presented here are all analytically computable. And in fact, I should say, to give credit, this is the only one that is actually our result. The other two are known results from other papers in the literature. Right, in general, you might not have a nice analytic form for your kernel, and you might need to do something like learn it via some optimization technique.
Okay, thank you.
Yep. Okay. So there was exactly one point where I cheated, and this is always where I cheat when I teach quantum field theory also. I slipped in a cutoff without you realizing. Okay. So in these experiments, notice the x-axis is log 10 of cutoff. Yeah. Why is that important? Well, let me give you one very concrete way to realize this. Let's just look at the tree level correction to the 4-point functions given by this. Yeah. Now, K's all have, in these particular architectures, have a constant piece. This constant piece, that constant piece, that constant piece. And in these architectures, what it leads to is that those K terms give you some constant piece. If the lambda is constant enough, it can get pulled out. And then these integrals are going from minus lambda to lambda, or really minus infinity to infinity before you realize you need a cutoff. So there are explicit divergences when you compute these correlation functions via perturbation theory, divergences that arise in the limit that the cutoff goes to infinity. So I'm going to do standard Wilsonian EFT. What is happening, of course, is that I have one set of neural network experiments that I'm trying to explain. I'm making the assumption that the cutoff is far above the input scale that I'm probing the system with. And in doing this, I now have a continuous one-parameter family of effective actions parameterized by lambda, where I'm just cutting off according to minus lambda and lambda. But I have one set of experiments to describe, right? Okay, so in the interest of time, I'll just mention that what I'm doing is standard Wilsonian renormalization. And so in particular, the correlation functions can't depend on the cutoff. Right? I have one set of experimental correlation functions to describe. I have a continuous infinity of S sub lambdas. And so if they're going to all work, I need that the correlation functions can't depend on the cutoff. I can extract the beta functions in the examples and compare to experiments. The beta function in ReLU-net is of this form. Notice that just like in quantum field theory, where the beta functions depend on the input dimension, here the input dimension, which is the dimension of the spacetime, here the input dimension enters directly into the beta function. And in my experiments for different input dimensions, 1, 2, and 3, I see that the slope is minus 5.02, minus 6.02, minus 7.04, etc. Right? So I'm minus 5, minus 6, minus 7 is exactly matching the slope predicted by my theory. Similarly for Erf-net, there's a story about non-constant couplings. And similarly for Gauss-net. So Gauss-net is this special translation invariant one. Okay, so right. So I can compute correlation functions. In computing correlation functions, I have to insert a cutoff so that I don't have divergences. But then I need to demand that the ability of the EFT to describe the correlation functions doesn't depend on the cutoff. Okay. Good. I'm leaving time to wrap up and make my crucial conceptual questions that are the most interesting things to me. I always want to make sure to say those. So the summary of the setup is that we're claiming that neural networks equals QFT, that there's a super sharp correspondence. Basically, the idea is that in the n goes to infinity limit, there's a central limit theorem that is guaranteeing that my neural network outputs are drawn from a Gaussian function space distribution. It's called a Gaussian process. Then if you back off and n is not infinity anymore, but some sufficiently large n, then I should have 1 over n suppressed non-Gaussian corrections in the effective action of the log likelihood. And when I do that, my correlation functions now pick up perturbative corrections from the interacting theory. This is quite general. Any standard architecture, to use Yang's language, and there's a long list of what that means, admits a GP limit. And sometimes that persists under training. So what we're hoping is that quite generally, QFT can be used to describe neural networks, both randomly initialized and during training, and ideally fully trained up to convergence. Okay, so away from the limit, we're using effective field theory. So output correlation functions can be computed as Feynman diagrams. We can measure some couplings in experiments, use those to make new predictions, and then verify those new predictions in experiments. That's the EFT pipeline that experimentalists and phenomenologists use. Wilsonian RG induces flows in the couplings, and this simplifies the model of the neural net distribution. And we verified all of this experimentally. Okay, so I want to give two comments. I really should delineate this. This is comment number 1, and the rest of the page is comment number 2. So quantum field theory is giving a function space treatment of neural networks. In this treatment, what is learning? It's always important to remember, like, what are our machine learning friends going to ask us? They're going to ask us, what is learning from a QFT perspective? Learning is the movement of the initial distribution to the trained distribution. And therefore, supervised learning, what is supervised learning? Supervised learning is the case where your function predicts pretty well once you've trained it, right? But really, if you have an ensemble of trained networks, you should be computing the ensemble average of the neural network outputs, the good predictions. And what is that? From our perspective, that's just the 1-point function, okay? So we're starting from some mean 0 initial distribution, usually, and then we're moving to some mean non-zero trained distribution. Supervised learning is learning the 1-point function, and often that will give symmetry breaking. Finally, this is related to overparameterization. So there's this question there's various ways to
Jim?
Yeah, go ahead.
You call that spontaneous symmetry breaking?
Yeah, I should cross this out. It could be explicit.
Because generally, I guess you think of the training examples as perturbing that distribution by some explicit potential.
Yes. Yeah. I should think of it probably as explicit. That's right. Yeah, probably. I should really remove that word. It's symmetry breaking, but it might be explicit.
Sorry, can I ask another question?
Sure, yeah.
Doesn't like the no free lunch theorem results tell you that the average over models like doesn't really give you much? Like I think of the no free lunch results as telling you that like your average case result for a given algorithm is not very good.
Yeah, but you'd really have to make sure to compare assumptions there to use no free lunch here. I mean, the thing that bothers me about that is, yeah, I don't know. I haven't thought about that concretely, but I'm working under the basic assumption that if I train 1 neural net or 10 or 100, that as I crank up to 100 trained neural networks, I shouldn't be. I should really be computing the average of the outputs of the trained outputs.
Yeah, I guess I'm just confused about whether the average that you're talking about is the same average.
No, yeah, and that's what I'm calling into question your assumption.
Yeah.
The same average.
Okay.
In my experience, I can train a neural network, like 100 of them or 10 of them. Okay, I've never trained. For the same parameters, I've never trained 100, but it's pretty common that I train 10 with the exact same parameters just to sort of test the robustness. And generally,
right. Yeah, I guess the no free lunch should be averaging over input parameters, I guess.
Yeah, that's right. I'm talking about averaging over the trained functions for fixed input.
Okay.
So if I have one image of a 3, right, one concrete image of a 3, and I have 10 neural networks that have been trained on MNIST.
Yeah.
I want to compute the ensemble of that average across all of those neural networks, all evaluated on that same 3 image. So I don't see that no free lunch applies there. Okay, so in some sense, to use some of our language, it's the function space perspective is kind of giving a dual perspective to the parameter space perspective, in the sense that as parameter space is getting more and more complicated, function space is getting simpler and simpler. So in particular, as one approaches the Gaussian process limit, you take this, for instance, this n goes to infinity limit, you're literally getting an infinite number of parameters in your neural network. More and more and more parameters. And yet, you have fewer and fewer important non-Gaussian coefficients in the distribution. All of the information in that network becomes trapped in the kernel in that limit. And so all of this non-Gaussian information just dies away. And so in this sense, as you have more and more parameters, the function space perspective gets simpler and simpler. That's kind of obvious given the results from the 90s in the literature, but Wilsonian RG adds another layer. Basically what it says is that distributions have an extra parameter, capital lambda, and by taking a limit in it, you can ignore even more coefficients. So even more important coefficients, so you have even fewer important coefficients in the distribution of highly parameterized neural networks. So there's two things in effect that are making the function space distribution simpler. One is that as n goes to infinity, fewer and fewer are important, but then Wilsonian RG will beat down some of the other ones as well. And so the reason that we sort of arrived at this point is that there was a particularly acute example of it in our experiments. So in one of the cases, a single number is all that it takes to correct the GP limit correlation functions to the NGP correlation functions, despite the fact that in moving away from the GP limit, you lost an infinite number of parameters. So this is really as far as I know, sort of the first work in this area. And to me, it's a really interesting idea to say, okay, if part of the reason we're getting confused about neural networks sometimes is because we're taking a tremendous number of parameters, the function space perspective is sometimes simpler, which is what we do, for instance, with like strong weak duality or something like that. We pass to the frame of viewing the problem where it's easier to treat what's going on. All right, so that's it. Okay, my timing's good, so thanks a lot, and I can go on for a little while if you guys have questions.
Thanks, Drew. Let's open the floor to questions. I have one.
Mm-hmm.
Are higher order terms, are they all suppressed uniformly by 1 over n, or are higher order terms suppressed by higher powers of 1 over n?
Right. That's a good question. We didn't analyze that directly. The one thing we did analyze, most of our experiments were at fixed n. The one place where we really varied n was in comparing to the GP. And in that case, we found that the leading correlations for the 4-point and 6-point functions, we only have 2 data points. Both of those go like 1 over n in the deviation, which suggests. Let's see. I'm working this out in real time. Right. Yeah. So there's an order lambda and an order kappa correction, but it could just be that the scaling of G6 was coming from the fact that the 1 over n-ness is coming from the lambda going like 1 over n without respect to kappa. So really, we haven't measured that. I can't say. I guess in general, I would expect the higher and higher it is, not quicker and quicker it's going to die, but we haven't shown that.
If you applied your formalism to these situations where the GP structure persists under training,
yes,
could you see like a flow between 2 free theories?
Yeah.
Is that what you would see? So training induces some type of flow. Do you have a good understanding of that?
Right. So let's ignore neural networks for a second. You can train just with Gaussian processes, right? So when you train with Gaussian processes, what's happening is that the mean and the covariance of the Gaussian process are getting updated so that you better map on to the data. Literally to the data that you're learning, that you're using to learn. So now suppose that I have a neural network that engineers some GP in the limit. Well, in the limit, if at initialization it's some known GP, then the Bayesian inference has to, if you're training via sort of standard Bayesian inference ideas, training via SGD is another question, then you should just have the same updates sort of in the GP limit, right? When you back off and you go to finite n, what you would probably do is just do SGD or atom or something like that. And in that case, as long as n is sufficiently large that you remain perturbative, then what you'll have is some sort of flow in the associated space of the FTs. But probably one of the hardest things there is the kernel updates. So the updates to lambda and kappa are just going to be some flows in lambda and kappa space. Note that these are not RG flows in the sense that we defined a minute ago, but the kernel could update to be some very non-trivial function, and that can vary widely, right? Yeah, so that's an obvious important direction forward. There were some papers in the ML literature, some really nice papers that got kind of close to some of these ideas that we've been thinking about. One sort of strategic thing that we tried to do differently was to really flesh it out at great length. So we made some choices. We said, we are not going to train, because to try to work these QFT techniques and do training simultaneously while telling people about Feynman diagrams and Wilsonian renormalization, it's just too much. So we have a full paper without any training whatsoever yet, but I think that this stuff can go in trained examples too. Whether you have an analytic expression for the kernel is another question, but you may not need it. So, yeah.
Thanks.
Yeah. Anyone else? Sorry that this comes fast.
Maybe you can remind me, Jim. So the kernel at the end of training, at least I guess in this sort of lazy training regime, is meant to be this neural tangent kernel. Is there an analytic expression known for the neural tangent kernel, or is that one just numeric?
The NTK, yeah, I need to reread the NTK paper, is the short of it. But the NTK is a kernel associated with training, right? So it's a. Can you say your question one more time?
Oh, I'm wondering, does the NTK not tell us what the right kernel function is at the end of training?
Yeah, I think that the NTK will tell you how to update also. But whether during the updates it maintains a GP, I think it does, but I don't really recall. Do you remember?
I thought it's still a Gaussian process at the end of training. It's just a different kernel function.
Yeah, I think that's right. So yeah, I really need to reread these papers. It's partially just my weakness because we haven't done it in our projects yet. So this is the NTK paper. The two papers that I'm citing here are NTK and Lee et al. But presumably in the NTK, they're really doing it in the infinite width limit. So it's GP to initialize GP to train GP with some flow induced by the NTK, right? I think that's what's happening. So so you're saying it's still GP when trained?
I believe so, yes.
Yeah, but I think that also makes the assumption that you're infinite to begin with. You're in the infinite width limit
yes.
to begin with, right? So yeah. I don't know. I haven't thought quite enough about training. The entirety of my training hopes for why this persists under training is just based on the idea that GP persists in the infinite limit under training. Yeah, you were there. I mean, part of this was inspired by Josh's talk in Microsoft last year, because they were doing all this great infinite width work, and there was sort of this immediate question, which is, what do you do at finite n?
What is the connection of the finite n corrections you're computing and those that was computed by Ethan and friends?
I need to remind myself what they
okay.
did. They were interested. Do you remember what exactly they computed, actually?
No, my memory is a little fuzzy, so I was trying to understand that they're computing the same corrections or slightly different ones.
Yeah, their analysis is a different sort of analysis. So they're often interested in asymptotics and sort of how the correlation functions are bounded in one way or another as you grow with n, whereas we're sort of just really interested in the correlation functions themselves. The short answer is I forget, honestly, their paper is great, but I forget the details of their paper. It was, we commented on some of the differences in our paper, but really it was Shoyaida's paper that came pretty close to what we wanted to do. So he had a nice paper last September or October or something like that. But,
yeah. I guess Sho is wanting to think about the RG in a very different way.
Yeah, so we commented on a number of reasons why, unless you make very specific assumptions, one probably shouldn't think of what he wanted as RG. So he was talking about there's this notion of pre-activation. So pre-activation is something that comes in as a GP itself. So at every layer in a deep network, there's some pre-activations. And the pre-activations have some distribution. And at finite width, those distributions are close to Gaussian processes. And in that case, right? So in that case, you could talk about the flow in the pre-activation distributions as you move deeper and deeper in the network. I think that's what he was after. But that's a very different RG flow than what we have in our paper. So for instance, normal notions of RG flow usually involve fixing the dimension of the QFT, for instance, and then varying the momentum or the cutoff scale. In his case, for instance, I'm trying to recall this particular point from the end of our paper that I wrote 2 months ago. But if you were to do something where you were to vary the width as a function of the depth, what the effective QFT description would be one that's changing dimension as you go deeper and deeper in the network. And it's definitely a flow, don't get me wrong. It's definitely like in spirit similar to RG flow, but our normal notions of RG flow are different from what he wants, at least as far as I could tell. So I really tried to, because he has this beautiful sort of inspirational story at the end of his paper where I think he even calls his section dreams or something like that. And his dream is that you can use RG ideas for understanding the pre-activation distributional flow. And so it's very similar in spirit, but I think it's not the normal RG flow that we would mean in physics. Whereas I think what we did at finite n is sort of exactly the sort of thing you would do in physics. It might actually be more interesting, but I think it's just not what we would normally call RG flow, in my opinion. So, but both of those papers are super good papers. But as is often the case, I forget details.
Normally we think about changing the cutoff as some way of sort of zooming in on low energy physics because we're performing low energy experiments. Yeah. Is there sort of like a principled notion of what the RG would be relevant for here in terms of like what is changing this cutoff doing for you? Yeah, right. So to do that, I should note first of all that our cutoff is an input space cutoff. Okay. So when you do these perturbative corrections in the non-Gaussian process, let me find a slide for you that actually does it. There we go. Nope. Here it is. Right. So this is the normal integral over interaction vertices that we would have in field theory. And here's my coupling constant. And the integrals go from somewhere to somewhere. And if you do minus infinity to infinity, you just get divergences. And of course, you can't compare to experiment. Normal old story. But we don't sweep divergences under the rug. We impose a cutoff, and then we demand RG conditions. And so in particular, in that case, the interaction vertex, if you will, is some input space point that is going to be cut off from some lower bound to some below some lower bound and above some upper bound. So how to interpret that depends a little bit on what type of data you're considering. Mike Douglas actually asked this question when we were talking about it. But let me give you an example. So like in MNIST, the input space, you have this 28 by 28 input space, right? And if you're doing grayscale, the entries are all integers between 0 and 255, right? So if you impose some cutoff in the input space, what it really is a cutoff on the brightness. So if you were to center the origin on the halfway point between 0 and 255 and then vary the cutoff, it's a case where you're only letting yourself consider interaction images, if you'd like, the analog of the input space points that have some maximal or minimal brightness. There's some brightness cutoff. But of course, if you have different types of data, the interpretation is going to differ. It's not going to be brightness, it'll be something else. So yeah. In general, it's input space, but how you interpret that depends on what is coming in of input. And it's in images, it's the brightness of the pixel. And if you have 3-channel images, the brightness of R, the brightness of G, and the brightness of B. Any last questions for Jim? Okay, well, let's thank Jim again. Good to see you all. Thank you very much, and hope you're doing well and staying healthy, and I wish you productive research despite everything that's going on. So,
Thanks a lot.